this video we show how ILLMO allows to analyze data from multiple subjects for the same experimental conditions. We even show how ILLMO can create several models, hence varying from purely within subject analysis all the way to purely across subject analysis, but also some intermediate models, and we will show how to decide which is the best model for the data. The data that we use is shown here. It's actually data for 8 subjects performing a Fitts law experiment, so the numbers are the time that people took to make a selection of a target on a computer screen, and the 9 conditions are 9 different ratios between the distance that they had to cover and the size of the object. And so this ratio is used in Fitts law as a kind of predictor for the average movement time. So we can read this data. And we can show that we have indeed read 8 different attributes. We could also read a pattern that we could use as a predictor. And according to Fitts law, we're actually not using this pattern directly, but we perform a logarithmic transformation on it. So once we read the attributes, as always, we get the log likelihood and the AIC, but since we have several subjects which share a common group name, we also get a log of the group AIC and LLC, so because they share the same group name. So one of the things we could do is actually use the pattern that we just had and connect it and use it as a predictor and use it for all. So we see that that decreases actually the group AIC. Now we could make that pattern, instead of deriving it from some independent variable that we have, to also create a pattern which is actually free to be optimized. Now patterns are determined up to a linear transformation. That means we have to fix 2 of the stimuli, and then the other 7 are just parameters that the program can optimize. So by default we fix the most extreme stimuli, which are 3 and 7 in this case. So by doing so, we see that the AIC goes down, and now we could start evolving, because we have a shared pattern that is shared by all subjects, and so which reflects the average perception across these subjects. But there's still a number of parameters that are actually specific for every subject, such as the standard deviation of the Gaussian distribution is being used. So we could make that into a group variable and see what that does. What you see is that the AIC goes down. So it's actually an improvement, especially if we, after we've done that, we've re-optimized the pattern. So here we see that that creates an improvement. So there's actually no point in having an independent standard deviation for every subject. We can just as well share the value. Like for any parameter, also if it's a group parameter, we still can create a log likelihood profile for it to decide its 95% confidence. We could do something similar for the gain, which is still also a private variable, and we make it into a group variable, which further decreases the log likelihood, especially if we re-optimize the pattern. So both cases, it seems that neither the standard deviation nor the gain, which can again also, the confidence of this can also be determined, there's any point in making them subject specific. Now there's only one parameter left that is subject specific now, that's the offset. Now what we can do is make that also into a group parameter, and you can see that that increases the value quite a bit. So there's no point doing this, so we actually send it back to its private variable. So if you look at the group AIC, we see that the best model is the one where all the parameters are shared except for the offset, which we can also see in the overview. If we go to the table, we see that the gain is the same value. The offset is still different, so we can also see that there are quite some distinct values from 0.5 to 0.8, so which is why we cannot share them, and the standard deviation has been made into a constant value.